So I want to introduce you today to maybe a causal approach to transfer learning that we've been developing now for a few years with Elia Sparenboim, my postdoc supervisor, as well as other students in his lab, Kashra, for instance, who was very important in developing some of the results I'll describe today. So I prepared around 45 minutes, so feel free to jump in with questions. If you have any, I'll try to stop also at various points. But I'm happy to make this as interactive as you'd like. So I guess to preface this talk, it's interesting to kind of revisit a little bit where we are as a field in machine learning. So in very general terms, we exist in this, let's say, vast research landscape that you can think of as kind of forests, right? In which progress has been mostly driven by empirical evaluations, data experiments, and their interpretation, right? And this is really becoming the main paradigm that we use to draw inferences. However, over the last 2-3 decades, even longer, not everyone agrees with this purely data-based perspective to understanding AI, data science in general, right? So you have, for instance, John Ioannidis, professor at Stanford, around 2001, pointing out that there's increasing concern that in modern research, false findings may be the vast majority of published research claims. From a slightly different angle, in the 1950s, the psychologist Donald Campbell points out that well-designed experiments, they demonstrate the effect that you're interested in study, but only for the very specific conditions that apply to the experimental or protocol in your particular study, right? Which includes everything from geographical locations, the kind of features of your individuals, historical moments, everything, right? And from a more conceptual perspective, you even have people in machine learning like Tom Mitchell, the founder of the machine learning department at CMU, saying that a learner that makes no a priori assumptions regarding the identity of the target concept has no rational basis for classifying any unseen instances. So the public discourse is very much about everything is data, but you have individual people, maybe small movements of different research lines that point towards data not being everything for drawing reliable inferences. And I guess we're familiar with this kind of sentiment in AI and machine learning as well, right? So we're used, for instance, of learning or training a classifier on some data collected in a particular environment, let's say a lab or some training domain, and then taking that learned model and using it for prediction of outcomes in some different domain. For instance, a test domain on patients or any application that you may like. And importantly, this new deployment domain may differ in multiple aspects from the training domain in which the model was developed in the first place. And it may be obvious then to point out that the optimal predictions in this training domain may not be optimal once deployed on our testing domain or on our test samples, right? And without some understanding of the relationship between these two domains, right, extrapolating, generalizing, or making reliable inference in general is going to be impossible. So beyond the data, you need, at least in the zero-shot kind of framework, you need to have some understanding of the relationship between training and testing. So now, I wanted to give you a little bit of a historical account, my own personal biased view of history to understand a little bit how this paradigm developed, and seeing a little bit the contrast between maybe two different paradigms in the data sciences. So on the one hand, you could go maybe back to the 1970s, where maybe a lot of this data-driven perspective in machine learning starts. So you have, for instance, Vladimir Vapnik and Alexei Bellot, with their own statistical learning theory that, really gave strong theoretical foundations for this learning principle, empirical risk minimization that permeates all of machine learning today. A little bit later, 1970s, 1980s, you had Paul Werbus developing the backpropagation algorithm, which was then popularized by Jeff Hinton, and with which you could really, implement this empirical risk minimization principle to learn complex models like neural networks, for instance. Then in the early 2000s, with regularization techniques developed by Rapti Pirani and Roger Earle, you were really able to kind of learn big overparameterized networks with this empirical risk minimization principle, right? And up until today, you have this movement, this revolution in deep learning and representation learning that really permeates most machine learning applications today. Right? And Joshua Bengio being maybe one, representative figure of this movement. So simultaneously, you could you can also think of a slightly different paradigm that goes from data-driven to more model-based. And this starts with Donald Campbell, at least in my view of things, around 1950s in psychology, where Donald Campbell and Junior Stanley were the first to develop this notion of external validity of experiments, right? So it's not only about the population in which the effects were developed, but it's really about thinking where are these inferences going to be applied. And they came up with a list of different criteria that your analysis needs to satisfy to claim external validity of your results. Then Lee Cochran kind of argued maybe against this particular framing that they had, and he put emphasis more on the interactions between the treatment and the context to justify, when a particular effect was meant to be extrapolated or not, right? And in my view, at this point, you start thinking more about mechanisms and a more model-based approach to justifying extrapolation. And so in the 1970s and 1980s, with the rise of causal inference, you started having pioneers like Donald Rubin and Judah Pearl, really systematically telling you how to deduce causal statements, for instance, from data and assumptions. So much more logical, much more formal approach was starting to be developed at that time. And for the setting of transfer learning, right, that kind of theory is known as transportability theory, which was developed maybe around 2010 or so by students of Judah Pearl. And as a final mention, extrapolation, thinking about mechanisms and when an inference is meant to be reliable or not, is also studied across many other fields of interest. For instance, Nancy Cartwright here is really, one big advocate for this mechanism-based approach to generalization and thinking about the causal powers, underlying a specific application, which is developed in the philosophy of science literature. Right. So in my take, where we are today is really that we've adopted many of the techniques from, let's say, data-driven accounts of machine learning to solve problems that would require a framing of model-based accounts, right? We're going into transfer learning problems where you need to think about, assumptions, the underlying mechanisms underlying the application, and not just the data. My personal framing, and don't read too much into this categorization. It's just one way of just describing things. Okay, so before I upset too many of you, I want to clarify a subtle point, which is that, of course, focusing on optimal training prediction is definitely worthwhile. Right? We see enormous gains in social, economic, and scientific disciplines by methods that really come from these data-driven paradigms. And so it's definitely worthwhile doing research and thinking in these terms for a lot of applications. However, in other applications, I would argue that if you neglect the context in which models are trained, that may be a limiting perspective, right? I guess whenever you cannot afford to be wrong, or you don't get to, if you're working on more critical applications that rely on you making correct inferences even across domains, you need to do a little bit more. Okay, so this was a little bit of an introduction. So I now want to get to the core of the talk, and really I'm going to talk about three different things. So first, I want to argue for this causal perspective to think about transfer learning in the machine learning context, and specifically a causal perspective on first evaluating the target error of a given classifier, right? You have a classifier maybe trained on some source domain that you may not know much about, or you may. You have some target error that you possibly don't observe a lot of data in, or maybe no data at all. Can you say something about the performance of this classifier if deployed in the target domain? And then we're going to use some of the results for evaluation to develop really an algorithm that would help you learn to optimize the target error in the first place. So can we learn, let's say, an optimal classifier for my target domain, even if, let's say, I don't observe a lot of data in it? Are there any questions at this point? Cool. So the setting for a lot of this work is a particular transportability problem, if you like, which is just a way of saying transfer learning with some data and structural assumptions about the commonalities between two domains. And the question I'll focus in this first part is really try to understand what's the error of a given prediction function in some target domain, given that you have data from a source domain, right? And mathematically, what I mean with this kind of statement is really the evaluation of an expectation, taking in a target distribution of some loss term that compares the predicted values given by your prediction function and the true outcome of interest, right? And so to make the contrast between this target distribution and the potentially source distribution that you have access to, we'll write a PT for target and PS for source. And so the learning problem in this case is try to evaluate this expectation given that you have some data from some source distribution, okay, and possibly also other things. And so the answer to this question is that sometimes we'll see that this kind of error can be computed, and critically, of course, it will depend on the invariances across the source and target domain. Right? So what I mean by structure or invariance across domains, I really have in mind a causal diagram like this one that is really meant to describe, it's a summary, if you like, an abstraction of an underlying model that is meant to generate the data in the first place. So this underlying model is formalized as a structural causal model that has a few key components. First, note that each one of the edges in the causal diagram is meant to summarize a functional dependence in the underlying model. So let's say X and Z here, diet and fitness routine, being, let's say, parents or direct causes of Y, the health outcome, means that both X and Z are arguments in the function that assigns value to Y. Okay? And in causal diagrams like this one, we abstract really of the influence of variables that you don't have access to. So these are these U variables that are meant to be unobserved and that capture randomness due to other sources. And whenever that randomness, those U terms are relevant to multiple variables that you do model, we express that with a bidirected arc that simply denotes a common cause or an unobserved confounder that simultaneously causes X and Z. So in this case, the bidirected arc refers to this variable u x z. That's an argument to the functions of both x and z, right? And so this, I guess, describes the structure of a single domain typically, right? Our MS, in this case, the source model. But we'll make use of a richer abstraction to both encode the structure of the source domain and tell you a little bit about the differences and commonalities that are expected to occur between the source and the target domain. So this richer abstraction is called a selection diagram, right? In which I've added these squared nodes to tell you really which ones of the mechanisms, which ones of these underlying functions in the structural causal model are meant to differ between two domains. So for instance, in this case, we really have that the target model is equivalent to the source model, except for the assignment of x and z. So potentially the function of assigning value to x in the target domain may be arbitrarily different to the one in the source domain, and similarly for z. And really the key assumption in these kind of diagrams is really all the places where there aren't any square nodes or there aren't any edges, right? Those are the features you'll be able to leverage to solve these kind of problems. So in this case, I guess the important bit is really that the function for y is meant to be invariant across the two domains. Okay, are there any questions with the formalism? Cool. So let's look at one simple example to understand really how these things translate into unique evaluation of error, let's say. So let's say that you're given some function, a prediction function, that takes diet as an input to predict an individual's health outcome, right? And you have access to source data from some source domain, right, on both diet, health, and fitness of your source individuals. And you also have access from the target domain you're interested in performing well in. But in this case, you don't have any information on an individual's health outcome. You only have diet and fitness information. And so let me just work through just a couple of simple derivations to show you how ultimately you can compute the error from the given information in some cases, right? So by definition, you can write the expectation as this weighted distribution, right? As this weighted sum with respect to the target distribution, which you can then manipulate a little bit to marginalize over z and then decompose the joint distribution in these two terms, right? And at which point you can use the assumptions embedded in the selection diagram to assert this equality between the conditional distribution of y in the target domain and the conditional distribution of y in the source domain. Right, so this follows by the invariance in the selection diagram. And now with just two simple manipulations of your original equation, you were able to express the target error as a function of things that you have access to. It's a kind of simple toy example, right? Just as an illustration of how these kind of transportability problems work. Are there any questions?
Yeah, hi. Can I just ask a question if you can hear me?
So I find it quite useful to think about success or failure in these kind of transportability problems
Hi,
in
sorry, Alexis.
terms of the underlying models that generate both the source data and the target data. So you can imagine that on the one hand, you have the space of all possible models for the target domain. These are all SEMs that you can imagine for a given set of variables. And on the other hand, you have all the possible errors that you might observe in this target domain. So here you typically have maybe positive numbers from 0 to infinity or something. That could be or depending on the domain of your variables, maybe something more restricted, but typically arbitrary. And so the first observation is that if you fix the model for the target domain, right, that entails a unique value of your error. You can take your target domain that's now fully specified. You can sample variables x and y, let's say. You can compute the loss function, compute the expectation, and you get a unique value. So SCMs entail values of errors given some prediction function. Now, what's interesting when you observe some data or you make some assumptions about the structure of your problem is that, well, in the first case, knowing the causal graph of your target domain, let's say, will constrain the space of possible models. Right, yeah.
Sorry, I'm just wondering, why can't you have multiple models that lead to the same error?
That's possible.
Okay, so it's not a unique mapping between one and error?
No. In fact, that will be very important.
Okay.
Yeah, no. I mean, in fact, often two models will lead to the same error, right? Which is going to be this notion of identifiability that people use in causality, for instance. So when you know something about your domain, for instance, you know something about the functional dependencies of your model, that will constrain the possible.
I think that's the question in chat. It says, how is conditional probability in the target and source domain invariant if the functions f, y are invariant?
Yeah. So let me go back to the. So here you need to do, I guess, to do it properly, you need to do a little bit more work, introducing the exogenous variables, marginalizing over them, at which point the functions will appear, because the conditional probability, also given the exogenous variables, is just a deterministic quantity which depends on the function. And once you have the function, then you can do this replacement between the function in the source domain, the function in the target domain, to work your way back to this equality between conditional distributions. So if you like thinking about this kind of stuff in a graphical way, the reason why these two things are equal is because the square nodes are kind of separated from y once you condition on x and z. That would be the graphical explanation. So yeah. Okay, so here now you're constrained to the causal models that agree with the particular causal diagrams that you take for your problem. And observing some data does really exactly the same thing. There's a subset of your models that are going to be compatible with your data that generate the data you observe, and that gives you further constraints. And so, whenever two models in your intersection, whenever all models in your intersection really map to exactly the same error value, right, we would say that our target error is uniquely computable. It's transportable in some way, right? And and this is really what underlies a lot of the transportability theory and the derivations that we saw previously. The reason why these kind of problem is solvable is exactly because of this, because all the things compatible with your knowledge really map to a unique value. And so I guess since 2012, 13, and so forth, there's Elias Barenboim's lab specifically has developed a lot of different algorithmic solution and graphical conditions to solve these kind of problems. And at this point, deciding whether a query like a target error is uniquely computable given data and assumptions is more or less a solved problem. That is, we have sound and complete algorithms that will give you the true answer, and will also give you the exact expression that you need to be computing. So if you're interested in a little bit of the background for this, these are 3 references that can be useful.
Just a quick question. What do you mean by compatible with the F part of your diagram?
Yeah, so by compatible, I mean that all the models that appear in this region, right, generate the observed data, right, your source data. So I guess in transportability problems, you typically talk about sets of models, right? You have a model for each one of the domains you have access to. And so saying compatible with data means that the set of models that you have generates your source data.
So they have the same distribution, joint distribution.
Yeah, exactly. Same joint distribution. Yeah. Okay, so in general, in the kind of transfer learning problems that we will be looking at mostly, you're typically not so lucky, right? Maybe you don't have a lot of understanding of the structure of the different domains you work with. Maybe the data you have isn't super informative. Maybe in the target domain you have no data, right? So typically the information you have in transfer learning problems isn't sufficient to really meaningfully constrain the space of models for the target domain that you may be working with, right? And so typically you're in this situation where two models compatible with your assumptions will evaluate to two different target errors. Okay, so typically the error isn't going to be uniquely computable, and there's going to be a set of values really that are compatible with your assumptions. The hope, however, is that the assumptions and the data you do observe do constrain the space a little bit, hopefully, right? So things aren't arbitrary anymore, but maybe they can be bounded in some sense. And this is the notion of partial transportability, analogous to the notion of partial identifiability for causal effects, in which really you're going to be looking at deriving possibly a lower bound and an upper bound on your target error. Okay, so in this diagram, just as a sketch, you have models, compatible models in the x-axis that evaluate different target errors, and you'll be looking at computing a maximum, let's say, right? And so I think the relevant notion for a lot of these transferring problems, or a lot of these evaluation problems, is really to understand to what extent you can estimate a maximum target error, right? And maybe do so tightly. That is, that your estimate is really a value, let's say, that some of the models evaluates to. So the kind of optimization problem we're looking at is really this kind of equation here. We're looking for the maximum over all causal models, of course, compatible with our assumptions and our data. So you're looking for the maximum value of your target error over this space. Okay, so is this clear? Cool. Right, and so now I guess we're going into a little bit of one of our contributions in this work is to show that this is possible, right? From a practical perspective, you can tightly estimate the maximum error of some prediction function if your observed variables are discrete. Okay. The discrete, I mean that your observed values, take values different categories, a finite set of different categories. And so the reason this is important is so looking back at our picture, right, where we have the space of all models, the constraints, and how these map to the possible errors that you might observe. If your observed variables are discrete, without loss of generality, you can operate on a subset of the models of the target domain, right? And here, there's a special subset that you can assume without loss of generality, which is a subset of SEMs that are parameterized by neural networks. So the functions are neural networks. And your exogenous distribution variables are univariate and uniformly distributed. So in some sense, the kind of claim that we're making here is that the this subset of models is as expressive as a set of all models, right? So you don't lose any information by using this particular parameterization. And so in particular, this means that you can search over this subset of neural models, if you like, and the maxima and minima will agree with the maxima and minima you would observe over the space of all models, right? So this is it's not an easy result, I guess, but it's really key. It allows you to solve this problem without really making any strong assumptions about the functional form of the distribution of your variables, right? So it's important here that we are operating in a fully non-parametric regime, right? The only assumptions we make is that we have some data and some understanding of the relationship between domains in the form of these selection diagrams. Okay. So this follows from, so you have analogous results for the setting of causal effect estimation and the estimation of counterfactuals that have been developed recently in a few years ago. And so if you're interested in the basis for these kind of claims, you have, let's say, more foundational treatments of these kind of results in these two papers. And so what's very interesting with this kind of parameterization is really that without loss of generality, you can search over this space of neural causal models and get some results that would apply to all models. And this is particularly useful because in practice, we have efficient tools to search over the space of neural causal models, whereas the space of all possible causal models is completely intractable, right? Are there any questions? So this is really an expressivity result, right? So let me show you how this works in a particular example, right? How, with an example, we have some data. How do we go about parameterizing our neural causal models, and then what kind of optimization problem we end up solving in practice? So let's take the colored MNIST dataset, which you might have seen. It's a relatively simple, and for us, it's kind of nice because there's a very kind of deterministic procedure to generating examples of this form. So you typically start with a grayscale image, right? A digit between 0 and 9. Okay. From that image, you produce a label, right? That's going to be 0 if the digit is less than 5, and it's going to be 1 if the digit is greater or equal than 5. And here we'll also introduce some noise, right? So with, let's say, probability of 0.25, the label is going to be flipped. Okay. So this function, this assignment of the label is kind of summarized in this edge, right? This is what the edge means. Now, once you have the label, you'll generate a color, right? You'll generate a color of red or green, with some probability, let's say, given the label. So typically in common examples of this colored MNIST dataset, there is one extreme domain, if you like, where most of the green colors are associated with a label of 1, and most of the red colors are associated with a label of 0. Right? So there's just typically a very strong correlation between our label and the color. And now, once you have the color and you have the grayscale image, you're going to deterministically generate a colored image of our digit, right, given the color that you generated. And so in these kind of problems, we're going to be interested in generating data according to different domains, let's say, different kind of variations of this setup. So we'll be working with a source domain in which we're going to fix this mapping of the color given the label to have a very high correlation between the color and the label, right? So in our example, we fixed this to be 0.9. Okay, and in particular, that correlation, right, is going to be higher than the correlation between the label and the grayscale image in our setup, which is going to be important later. And now we'll have some data from this particular source domain, and we'll be interested in evaluating some prediction function in a target domain from which you don't observe any data, and in which you're told that all mechanisms are equivalent to those of the source domain, but the assignment of the color is potentially arbitrary. Right? So in particular, this correlation between the label and the color may be completely different in our target domain. Okay. Maybe it's the completely opposite color. Maybe the color is assigned randomly, right? So you don't know. And so the question at this point is, let's say, given some classifier, right, that takes the colored image and predicts the label, can we take our data, take our assumptions to try to understand the performance of such a classifier in a hypothetical target domain of this form, where you have these kind of variations? And so I told you that to evaluate these kind of things, we're going to instantiate some neural causal models that will parameterize according to our special parameterization. And so the diagrams really tell you a lot of information for this. So the diagrams will tell you exactly what are the functional dependencies that you should have in your neural causal models. And so, for instance, in this particular example, we know we will have two different models, one for the source domain, one for the target domain, in which, for instance, the assignment of y is going to be a neural network that takes the grayscale image as an input and also some independent noise. The color is going to be a neural network that takes the label as an input and some independent noise, and so forth, right? You just follow the causal diagram to define your parameterization. And I guess the one important part here is that the neural networks in the source and the target domain are meant to be really exactly the same. It's meant to be exactly the same function, except for the neural network that assigns value to color, in which the parameterization may be completely different. So in practice, we have two sets of parameters, one for the source domain and one for the target domain. And so, okay, at this point, you have your model. And and your model kind of by design or by construction really satisfies the structural constraints that you have, right? It's really designed to mimic the causal diagram. So that constraint is fine. And now for these models, for these class of models, we're interested in finding the model that maximizes the target error and also simultaneously is a model that generates the source data, right? So your source neural causal model, right, the one on the left, if you generate some data according to these functions, you're meant to recover the distribution of the source domain. So you're really set up with a constraint optimization problem in which, on the one hand, you want to make sure that your models generate the observed data, and on the other hand, you want to be looking for the model that maximizes our target quantity. And it's really not more difficult than this, right? In the infinite sample regime, if you have enough capacity and everything, you're going to be guaranteed to converge to the tight maximum error for your problem. And so there's a typo here. H of x should be h of z, sorry, which is the function we're evaluating. Are there any questions at this point? Cool. So in a way, with the procedure I just described, we have a way and methods, here represented with this magnifying glass, that really is able to tell you the maximum target error of any classifier. Okay, so we have this tool that can, find you the maximum error for every function you give it as an input, subject to our assumptions and data, or at least in principle, right? Finite sample considerations aside. But this is great, but ultimately the objective, now moving on to the second part of the talk, is really understanding which ones of these classifiers evaluates to the lowest maximum target error, which ones of our possible classifiers has this kind of best worst case guarantee. So this is going to be the optimization problem, in which we're going to be interested to search over our space of classifiers to find the one that minimizes the maximum target error. So the maximum target error part is taken care of with this previous procedure, and now we're going to be looking at finding a way of efficiently searching in the space of functions. So to do so, note one interesting thing is that as a byproduct of our evaluation procedure, we not only evaluate the maximum target error, but we also recover the neural causal model, right, that entails this target error in the first place. So we have a way of generating adversarial data, if you like. You can take this model. The data it generates is going to be the kind of data set that leads to the worst case error of some classifier. Okay, so you can so this is important, and so now I'll describe kind of an iterative procedure where you can leverage this adversarial data to slowly converge towards a solution that is going to do well across all possible adversarial data sets, if you like. So start with maybe a randomly initialized prediction function. This could be some neural network or your favorite architecture. You take this prediction function, you pass it through our evaluation procedure, right? That is at that point going to give you a model that entails the worst case performance of this initial prediction function, right? So from this model, you can sample some data that we'll call D1. At this point, in a second iteration, you're going to train now a second prediction function that is designed to minimize error in this adversarial data set that you've sampled in our first iteration. Okay, so you have in the second iteration a classifier that performs well on this data set D1. And you can then repeat the procedure, right? You take this new prediction function, you pass it through our evaluation procedure, and you ultimately get a second sample of adversarial data that is meant to represent the data set that in our class of possible data sets for the target domain in which H2 does the worst. Right. And in a third iteration, one thing you can do is then take the two data sets you've generated so far and minimize for maximum error across these two data sets. Okay. So we're playing a little bit of a game here, right, between an adversary, which is our evaluation procedure that generates adversarial data, and then a learner that is, over several iterations, try to minimize worst case errors across all of these data sets we're generating. And so at this point, you have a little bit of a guarantee for H3, right? You know that your H3 is going to be the worst case predictor across the two data sets you've generated so far. And if you do this a sufficient number of times, okay, you're kind of guaranteed to converge to the prediction function that minimizes the maximum error over all possible causal models. Okay. So you can think of this maybe graphically, in which you have a space of possible distributions for your target domain, and you have a method of generating the most difficult distribution in sequence, right? And the more distributions you generate, the more robust is going to be your classifier that you're training at each iteration. And you'll reach a point in which your classifier is guaranteed to be the best worst case classifier across all possible distributions. Okay. So let me go back to the colored MNIST data set to show you a little bit how this procedure would work in that case. Okay. So remember that we're working with these colored images. We have access to data from some source domain, and we're interested in doing good prediction in some target domain in which this color correlation with the label could be arbitrary. So we start with a randomly initialized predictor. Okay, so what you see here is the important bit is the y-axis, which is the error in the target domain, right? And on the x-axis here, you have different iterations of our evaluation procedure. Okay, so typically it's going to be interesting to look at the last point of this evaluation procedure, which is, you can think of as convergence. So what this particular panel shows you is that a randomly initialized predictor has an error of 0.5 in the worst case distribution for our target domain. Okay, this is what this is telling you. From this converged worst case distribution, we can retrieve the model and generate some data. So this is what the data looks like for this particular worst case model, right? Just colored images with some label. And it's interesting to note here, for this particular example, we find the model generates with a strong correlation between the color and the label. So here, all of the green ones are labeled with 1, all the red ones are labeled with 0. So now you have this data set, you're going to go through the second iteration of our algorithm, which is training a classifier on this data set. And so you can see already that this classifier is going to exploit this correlation between the label and the color to produce really something that predicts based on the color. And so when you now evaluate such a classifier, right, you see a very different pattern. So now the worst case error jumps to 1, which makes sense, right? Because I'm able to generate data sets in which the correlation is completely flipped. And for those data sets, the error is going to be close to 1. And this is exactly what you see here, right? So this is a sample from the worst case data set for this particular classifier, in which you can see that all the red images now are labeled with 1 and all the green ones are labeled with 0. Okay. This is fine. Let's continue, right? We're now gonna go onto our third iteration of the algorithm, which is to train a new classifier to minimize the maximum error across these two data sets. Okay, these two data sets I kind of have opposite correlations between the label and the color. And you can see already what the kind of behavior that you'll see if you train for minimum maximum error, for these over these two data sets, is that to do good prediction, you kind of have to you cannot rely on the color as an indicator for the label, right? You're kind of forced to be using the digit for predicting the label. And this is exactly the kind of behavior that we're trying to encourage with this procedure. And so in this third iteration, this new classifier has a very different performance profile, right? So we reach an error of approximately 0.25, okay? And knowing how all of this was generated, because we did it ourselves, this is meant to be theoretically optimal. This is meant to be theoretically optimal because the label was produced from the digit, correctly with probability 0.75. That is, there's going to be an error of 0.25 for the optimal kind of procedure. And this is the kind of predictor we converge at in the third iteration. Okay. So you can see here the last point on this curve is meant to be, the worst case error this particular predictor. Right. So this was a little bit the kind of conceptual description of the kind of predictor we're meant to converge with, which illustrates really our more maybe theoretical guarantee that if you do this enough times, you converge to really an optimal classifier in terms of worst case performance. Are there any questions? Okay, I have just a few minutes to wrap up. So I think I'm more or less on time. Okay, so to conclude, I guess, I mean, I'm a huge fan of all of the advances we've been seeing in this new deep learning revolution, and really data is amazingly powerful to solve a lot of problems, you know, that have tremendous economic value. But ultimately, I do worry that the data we observe is only a reflection, you know, of a particular experiment, a particular domain, a particular set of individuals that generated the data in the first place, right? And you need to take this seriously if you want to solve, you know, a broader range of maybe more complex problems that don't necessarily relate to the exact population that generated the data in the first place, but are more general, right? Maybe they relate to a different population, or you want to make a more general statement. And so hopefully, with this maybe causal perspective, you know, that integrates a lot of the elements of modern machine learning, right? Efficient training, you know, differentiable optimization objectives and models, and you know, presumably that you could really scale up to high-dimensional variables and so forth, both for evaluation and for optimization. Hopefully, you can take some of this and think about going back from the data to the underlying system that generated it in the first place or others, and still make you know, reliable inference with some kind of theoretical guarantee. So that is everything for me. Thank you very much.
Those online, can you put a question in the chat? Any questions?
I might have missed it, but so how does it scale with the, because you mentioned, okay, this works for discrete random variables, right? Discrete. How does it scale with the number of categories?
Oh, how does it scale with the number?